Good morning, everyone. Today I want to share with you one of the most fascinating puzzles in the history of mathematics, a problem so counterintuitive that it sparked a national controversy, humiliated tenured professors, and made a woman with the world's highest IQ the target of thousands of angry letters. Picture this. You're on a game show, 3 doors, 1 car, 2 goats. You make your choice, the host reveals a goat, and then offers you a chance to switch. What would you do? Most people say it doesn't matter, and most people are spectacularly, provably wrong. By the end of this talk, you'll understand exactly why, and you'll never see probability the same way again. Here's our roadmap for today. We'll begin by setting up the puzzle exactly as it appeared on the game show Let's Make a Deal. Then we'll confront our intuition head-on and diagnose exactly why it fails. After that, we dive into the mathematics, a crystal-clear proof by simple enumeration that requires no advanced training whatsoever. We'll connect it to Bayes' theorem and the deeper principles of conditional probability. Then comes the drama, the extraordinary 1990 controversy that saw 1,000 PhDs publicly embarrass themselves. And finally, we'll extract the real-world lessons this puzzle offers for anyone who makes decisions under uncertainty, which is to say, all of us. Let's set the scene properly. It's the 1970s, and you're a contestant on Let's Make a Deal, the hit game show hosted by the legendary Monty. 3 identical doors stand before you on a brightly lit stage. Behind one door is the prize of a lifetime, a gleaming new car. Behind the other 2, goats. You point to a door, let's call it door 1. But here's the crucial twist. Monty knows exactly what's behind every door. He's the host. He's seen the setup. Before revealing what's behind your door, Monty walks over to one of the other doors, door 3, say, and opens it to reveal a goat. Then he turns to you with that famous grin, the audience goes wild, and he asks, would you like to stay with door 1, or would you like to switch to door 2? This is the Monty Hall problem in its purest form. Now I want you to honestly ask yourself what you would do in this moment. 2 doors remain. One has a car, one has a goat. It feels exactly like a coin flip. Your intuition is practically screaming at you. Monty eliminated one losing option. You're left with 2 equally likely doors, so it's 50-50. Why would switching possibly help? And here's the thing, you'd be in excellent company thinking this way. This is exactly what nearly everyone concludes, including people with advanced degrees in mathematics. But the truth, verified by both mathematical proof and countless computer simulations, is that switching doors wins 2/3 of the time. Your intuition isn't just slightly off, it's catastrophically wrong. Let that sit for a moment. Let's compare the 2 strategies side by side, and the logic is devastatingly simple. If you stay with your original choice, you're essentially betting that your first guess, made when you knew absolutely nothing, happened to be the winning door. What are the odds of that? 1 in 3. You win only if you were lucky at the very start. Now consider switching. You switch when your first pick was wrong. And what are the odds your first pick was wrong? 2 in 3. Because 2 out of the 3 doors hide goats. When you initially pick a goat, which happens most of the time, Monty is forced to reveal the other goat, and the remaining door must be the car. Your initial wrongness becomes your winning strategy. Switching literally doubles your chances. Now we enter the realm of proof. This isn't a matter of opinion. This isn't philosophy. This isn't one of those puzzles where reasonable people can disagree. The Monty Hall problem has a single, definitive, mathematically provable answer. And here's the beautiful part. You don't need advanced degrees to follow the proof. The argument is so elegant, so simple, that once you see it, you can never unsee it. And you'll be able to explain it to anyone in under 2 minutes. Let's walk through it together. Here's the proof by enumeration, and it's so simple a child can follow it. There are exactly 3 equally likely worlds corresponding to where the car is hiding. In scenario A, you initially picked the car. Monty reveals either goat, he has a free choice, and if you switch, you lose. That's one losing scenario. In scenario B, you pick goat 1. Now Monty has no choice. He must reveal goat 2 because he can never reveal the car. You switch to the remaining door, which is the car. You win. In scenario C, you picked goat 2. Monty must reveal goat 1. You switch to the remaining door, again the car, you win. Count them up. Switching wins in 2 scenarios, loses in 1. 2 out of 3. No equations, no advanced probability theory, just counting. The key insight is that Monty's knowledge constrains his behavior. He's not acting randomly. So what does this mean in practice? 2/3. That's the probability that switching doors puts you behind the wheel of a brand new car instead of standing next to a goat. Your odds literally double from a 1 in 3 long shot to a 2 in 3 favorite with a single decision. Ask yourself, in what other game can you double your chances of winning with one simple action? This number is the beating heart of the Monty Hall problem. It's not an estimate, not an approximation, not a matter of interpretation. It's a mathematical certainty that follows directly from the rules of the game. And yet, as we're about to see, 1,000 PhDs couldn't bring themselves to accept it. Let's visualize the comparison. When you stay, your win probability is exactly 1/3, 33.3%. When you switch, it jumps to 2/3, 66.7%. That bar on the right is literally twice as tall as the bar on the left. And remember, these are not estimates, not approximations, not rough guesses. These are exact probabilities derived from the complete enumeration of possible outcomes given the rules of the game. The math doesn't care about your intuition. The math doesn't care about your credentials. The math is simply immutably true. And this is precisely where the story gets explosive. Because in 1990, a lot of very smart, very credentialed people refused to accept what this chart plainly shows. And now we arrive at one of the most extraordinary episodes in the history of popular mathematics. A Sunday magazine column called Ask Marilyn, a woman with an IQ of 228, the highest ever recorded, and an academic firestorm that revealed something deeply unsettling about human reasoning. This isn't just a story about math, it's a story about intellectual humility, about the limits of expertise, and about what happens when deeply held intuitions collide with irrefutable proof. In September 1990, Marilyn Savant, already famous for holding the Guinness World Record for highest IQ at 228, published the correct solution to the Monty Hall problem in her Parade magazine column, Ask Marilyn. The response was nothing short of volcanic. The magazine received nearly 10,000 letters. About 1,000 of them came from people holding PhDs, mathematicians, statisticians, engineers, scientists, many writing on official university letterhead. They didn't just disagree with her, they mocked her, they belittled her. They told her to go read a textbook. Even Paul Erdos, one of the most prolific and celebrated mathematicians in history, flatly refused to believe the answer until he was shown a computer simulation. Parade magazine, responding to the unprecedented uproar, published 4 separate follow-up columns on this single puzzle, something they had never done before and have never done since. Let that sink in. 1,000 PhDs were wrong, and the woman with the Sunday puzzle column was right. Let me read you one of those letters, and I promise you, this is real. A PhD mathematician writing on professional letterhead sent this to Marilyn Savant. May I suggest that you obtain and refer to a standard textbook on probability before you try to answer a question of this type again? Read that again. This condescending letter was sent to a woman with the highest recorded IQ in human history, and she was right, and he was wrong. And the proof was sitting right there in his own undergraduate probability textbook. The Monty Hall problem isn't just a math puzzle. It's a mirror held up to human nature. It shows us how even the most educated, most credentialed minds can be utterly enslaved by intuition, and how difficult it is, even for experts, to accept a truth that violates what feels obvious. We've seen the math, and we've relived the controversy. Now let me show you why this matters far beyond a 1970s game show. Because here's the uncomfortable truth. You face Monty Hall problems every single week, and you're probably getting them wrong. You just don't realize it. The same cognitive trap that made 1,000 PhDs write angry letters to a magazine is sitting inside your next medical test result, your next investment decision, your next strategic choice at work. Let's pull back the curtain on where the Monty Hall logic hides in plain sight. Consider a routine medical screening. Your test comes back positive. You panic. But if the disease affects only 1% of the population and the test has a 5% false positive rate, what are the odds you actually have it? Not 95%, closer to 16%. That's the Monty Hall logic at work. The new information, the positive test, doesn't replace the base rate, it updates it, exactly like Monty opening a door doesn't flatten the odds to 50-50. In investing, when quarterly earnings surprise the market, your prior beliefs about the company need Bayesian updating, not abandonment. In the courtroom, each piece of evidence should shift your confidence incrementally, not flip the whole case. The Monty Hall problem is a masterclass in how to think when the world gives you partial information, and the world almost always gives you partial information. So, here we are at the final door. The Monty Hall problem has been called a paradox, but it's not. It's a mirror. It shows us our own cognitive wiring, our resistance to updating beliefs, our preference for the comfortable choice we already made. Marilyn Savant was right in 1990, and she's still right today. The math hasn't changed. What can change is how you respond to new information. Next time the evidence shifts, in your career, your investments, your relationships, ask yourself, am I staying with door number 1 out of conviction or out of stubbornness? Because the numbers are clear. Switching wins, not just on let's make a deal, in life. Thank you.